Tesla just replaced part of its Fremont car factory with production equipment for Optimus. Cybercab has entered production in Texas. And Tesla spent $5.8 billion in a single quarter as it builds the factories, chips, batteries, and AI compute behind its autonomous future. Then Elon Musk issued the warning that changes the story. Optimus may be the hardest product Tesla has ever tried to manufacture. Walking is not the real test. Tesla must give the robot useful hands, train it for an unpredictable world, make it safe around people, and manufacture entirely new components at a cost that produces an economic return. Here are the 5 bottlenecks between an impressive demonstration and a robot business, plus the evidence that will tell us whether Optimus becomes Tesla's next great platform or its most expensive science project. Revenue reached $28.2 billion, up 26% from a year earlier. Vehicle deliveries hit a second quarter record. Active FSD subscriptions grew to 1.48 million. Energy storage deployments rebounded sharply, but operating income fell 57% to just under $400 million. Operating margin dropped to 1.4%. Capital spending surged to $5.8 billion, and free cash flow turned negative by about $1.1 billion. Those figures do not mean robots caused Tesla's margin pressure. Tesla points to several factors, including AI and other research spending, stock compensation, lower regulatory credit revenue, and lower vehicle pricing. Tesla is no longer funding a few experimental robots in a laboratory. It is building an industrial system around autonomy, compute campuses, dedicated factories, battery capacity, semiconductor plants, data operations, and entire vehicle and robot production lines. So the question is no longer whether Tesla can make an impressive prototype. It is whether Tesla can turn physical AI into a repeatable business before the cost of the build-out overwhelms the returns. Tesla's quarterly deck makes an important distinction that gets lost online. Cybercab has begun production at Gigafactory, Texas. Engineering test drives of production vehicles have started on public roads, and employees have begun taking rides on the factory campus. Tesla lists more than 125,000 units of installed annual Cybercab capacity, but the company also warns that installed capacity is not the same thing as the current production rate. A factory can contain equipment designed for a certain output long before it reliably produces that number of finished vehicles. Optimus is earlier. Tesla has decommissioned the Model S and Model X lines at Fremont and is installing first-generation Optimus equipment. Construction is also underway in Texas. The first builds are supposed to feed what Tesla calls the Optimus Academy, where robots can collect training data and develop more useful functions. But the official status is construction, not mass production. There is no disclosed commercial delivery count, utilization rate, unit cost, or customer revenue. This is the precise point where robot hype meets industrial reality. The most important part of a humanoid robot may not be its brain. It may be its hand. Human hands combine strength, delicacy, tactile feedback, and an extraordinary ability to adapt. We can pick up a heavy box, thread a cable, turn a key, separate 2 thin sheets of paper, and catch an object that starts to slip. A robot can succeed in a demonstration when the object is placed in a known position and the movement is practiced repeatedly. A commercial robot has to succeed when the object is rotated, partly hidden, damaged, wet, flexible, or handed to it by a person who behaves unpredictably. That is why dexterity is not a cosmetic feature. It determines how many economically useful tasks the robot can perform. If Optimus can walk through a factory but cannot reliably connect a cable, sort irregular parts, load a machine, or recover after dropping something, its addressable workload collapses. The hand is where mechanical design, sensors, control software, and AI collide. Language models operate inside a digital environment. A wrong answer is frustrating. A physical mistake can break a product, stop an assembly line, or injure someone. Factories are more structured than homes, which is why they are the logical first market. But even a factory contains glare, shadows, blocked pathways, carts in the wrong place, parts arriving out of sequence, and people stepping into the robot's workspace. The robot cannot simply memorize every situation. It needs to recognize what changed, choose a safe response, and recover without waiting for an engineer. Tesla's advantage is that it has spent years training vision-based systems for cars. It understands large-scale video data, neural network training, and deploying software to a fleet. But driving and manipulation are not the same problem. A car operates on roads with defined rules and limited control outputs. A humanoid has many joints, 2 hands, contact with irregular objects, and an almost unlimited number of possible tasks. The number of ways it can fail expands dramatically. A viral robot clip may last 30 seconds. A useful industrial worker needs to operate for thousands of hours. That means the critical metrics are not how fluid the demo looks. They are intervention rate, task success rate, uptime, maintenance cost, and safe recovery. How often does a human need to rescue it? How many attempts does a task require? What happens when a sensor fails, a joint overheats, or a person enters its path? And can it fail safely while holding a sharp tool or a heavy object? Tesla can test Optimus inside its own factories before selling it to outside customers. That is a major strategic advantage. Tesla becomes the developer, the manufacturer, and the first customer. If you want the evidence behind the robot and AI headlines, subscribe to Future Signal. We separate real deployment from demo hype every week. When Tesla begins reporting hours worked, tasks completed, human interventions, and cost savings, Optimus will be moving from demonstration to business. Until then, production line construction is a leading indicator, not proof of commercial success. Tesla did not invent the automotive supply chain. It rebuilt and vertically integrated parts of an enormous existing industry. Humanoid robots are different. There is no mature global supply chain capable of delivering millions of standardized humanoid hands, compact actuators, specialized gearboxes, tactile sensors, batteries, compute modules, and safety systems at automotive cost and quality. Tesla may have to design many of those components, qualify suppliers, build tooling, create testing systems, and sometimes manufacture parts itself. The company is already connecting this problem to a much larger infrastructure build-out. Tesla says its 2 Texas AI clusters now exceed 200 megawatts of installed training compute capacity. Cortex-2 supports both vehicle and humanoid autonomy. Tesla is also preparing an Austin semiconductor facility intended to strengthen long-term access to logic and memory chips. This is why the Optimus story cannot be separated from NVIDIA, memory suppliers, chip packaging, batteries, and manufacturing equipment. A robot is a walking stack of constrained technologies. One missing component can slow the entire ramp. The transition from prototype to product destroys easy assumptions. Expert technicians can hand adjust an early robot until it performs well. A production line has to build thousands of units whose joints, sensors, wiring, and software all behave within tight tolerances. Every additional component creates another possible failure point. Every new manufacturing step slows the ramp. Every custom part must eventually reach a cost that makes the robot cheaper than the work it replaces or enables. Tesla has a genuine advantage here. Few robotics startups have designed factories, managed global suppliers, built batteries, trained large AI systems, and serviced millions of machines. But Tesla's automotive experience does not automatically solve humanoid manufacturing. It simply gives the company more tools and more capital to attack the problem. Cybercab may be the most important bridge in Tesla's strategy. It gives Tesla a nearer-term test of autonomous operations, producing dedicated hardware, deploying it into a fleet, monitoring safety, handling maintenance, and earning revenue from work performed by a machine. Robotaxi is also further along than Optimus. Tesla reports paid miles, active cities, and a growing FSD subscriber base. That creates evidence investors can measure, but the cautious rollout also reveals the central rule of physical AI. One serious failure can trigger public backlash, lawsuits, and regulatory restrictions. That lesson becomes even more important when the autonomous machine has arms and works beside people. If Tesla learns how to operate Cybercab safely and economically, parts of that operating system may transfer to Optimus, fleet monitoring, remote assistance, data collection, maintenance, insurance, and continuous software improvement. The products are different, but the business machinery around them may rhyme. The strongest case for Tesla is not that Optimus will become human level next year. It is that Tesla can start narrow, deploy robots inside its own factories, collect proprietary data, improve the hardware, and expand task by task. Tesla does not need a robot that can do everything on day one. It needs a robot that can perform a small number of valuable tasks reliably enough to save more money than it costs. If that happens, Tesla gains a self-reinforcing system. More robots create more data improves the software, better software unlocks more tasks, and more useful robots justify larger factories. The risk is that the last 10% of performance contains 90% of the difficulty. Optimus may look increasingly capable while remaining too unreliable, too slow, or too expensive for broad use. Specialized machines may outperform humanoids in factories, Chinese competitors may reach lower hardware costs faster, and billions of dollars in compute, factories, and custom components may arrive years before meaningful robot revenue. Tesla can afford ambitious bets, but negative free cash flow and a 1.4% operating margin make execution more important, not less. The market may value the destination long before Tesla proves the route. Ignore the next dancing video for a moment. Watch for 5 concrete signals. First, does Tesla move Optimus from construction to production in its official reporting? Second, does it disclose how many robots are performing real work inside Tesla facilities? Third, does it report task success, intervention rates, uptime, or measurable labor savings? Fourth, does unit cost fall as the first-generation line ramps? And fifth, does Cybercab expand safely while generating meaningful paid miles in fleet economics? Those signals will tell us far more than another polished demonstration. Tesla has not solved the humanoid robot, but it has crossed an important line. It is replacing old vehicle production space, installing robot equipment, building enormous AI infrastructure, and spending at a level that turns the idea into an industrial bet. The world's most valuable robot may not be the one with the most impressive demo. It will be the one that can perform useful work, safely, repeatedly, and cheaply enough to justify building the next million. Tesla believes it can be that company. Now it has to prove it. Which matters more in the robot race, Tesla's manufacturing experience or a competitor that solves dexterity first? Tell us which side you are on and why, and if you want to see how NVIDIA plans to become the infrastructure beneath this entire robot industry, watch our breakdown on screen now, subscribe to Future Signal, and I will see you in the next one.